Hello again, and welcome to our lecture on elementary probability. Last lecture, we looked at some counting principles. We talked about permutations and combinations. And in this lecture, we'll take those ideas and talk a little about probability. Questions like, what are the odds? What's the probability of rolling a 7 with a pair of dice? Or what's the probability of winning a lottery? These are great questions, I think, very practical questions. And most pre-calculus courses, both at the high school level and the university level, spend usually a week or two on probability theory. I think one reason is it's a lot of fun. I think students enjoy this. And also in calculus courses, many of the applications of calculus deal with ideas of probability. Furthermore, as I probably said last lecture, if you go on in mathematics and take calculus and after calculus, there are probability courses that require a full 3 semesters of calculus to be successful. Higher level probability is based on calculus, actually. But don't worry here. We're going to be doing some very elementary probability using our counting principles. And one of the fun problems we'll do at the end of the lecture is a very famous birthday problem, it's called. So I think you'll like that problem a lot. Okay, let's develop some vocabulary first in probability theory. And let's suppose the following scenario. I have a single die, a 6-sided die, and I throw it onto the ground. And the result of that experiment is uncertain. A 1, 2, 3, 4, 5, or 6 could show up. There are 6 possible, what we call outcomes. And the set of all the outcomes is called the sample space. So in this example, the sample space would be 1, 2, 3, 4, 5, 6. It would have 6 elements in it. And a subset of the sample space is called an event. So an event is a subset of the sample space. Let me show you some elementary examples. You toss that 6-sided die, and what's the sample space? Well, as we said, it's the set 1 through 6. Let's ask a probability question right away. What's the probability of tossing a 4? Well, I think you see what's going on here. The event of tossing a 4 can occur once out of those 6, so it's 1 out of 6. What's the probability of rolling an even number? Well, 2, 4, and 6 are even, so there are 3 even numbers, so that would be 3 over 6, or a half. Okay, here's even a simpler sample space. You toss a coin in the air, and it lands head or tails. What's the sample space? Well, you could describe it as heads or tails, or H, T. It has 2 members in that sample space. What's the probability of a head? Well, of course, it's just 1/2. So you see these ideas are fairly straightforward. The definition of the probability is you take the size of the sample space, and that would form your denominator. And in the numerator, you take the size of the event under consideration. And it's that quotient that is the probability. Let me show you another example of that. Now we'll toss 2 coins. Okay? So we toss 2 coins. What's the probability that both land heads up? Okay, to answer that question, let's first figure out what the sample space is. So I toss the 2 coins, and the possible outcomes are head, head, tail, tail, head, tail, or tail, head. So the sample space has 4 elements in it. HH, HT, TH, and then TT, meaning tail, tail. Okay, what event are we interested in? We're interested in both coins landing heads up. And there's one, that's an event with a single event. So the probability will be the size of that event, 1 divided by the full sample space, 4, so the probability is 1/4. Here's the formal definition. If an event E has n of E equally likely outcomes, everything has to be equally likely, like tossing coins, the outcomes are equally likely. And its sample space S has n of S equally likely outcomes, then the probability is the quotient. n of E divided by n of S. The size of the event divided by the size of the sample space. That's the probability. That's the definition of the probability of the event E. Let's do some examples. Okay, now we'll have 2 dice. We roll 2 dice. What's the probability that a 7 is rolled? Well, think of the ways you can get a 7. I claim there are 6 possible outcomes that produce a 7. Well, here's how you could think of it. The first die, there are 6 possibilities, aren't there? And the second die, there are 6 other possibilities. So all told, there are 36 possible outcomes here. So the sample space has 36 possible outcomes. But to get a 7, you have to roll the dice, a little bit special. For instance, you might roll a 1 with one die and a 6 with the other, and that produces a 7. Or you could roll a 2 and a 5, or a 3 and a 4, or a 4 and a 3, or a 5 and a 2, or a 6 and a 1. And those are 6 total events that give a roll of 7. Okay, so the probability of rolling a 7 would be 6 divided by 36. The size of the event, which is 6 possible outcomes, divided by the size of the sample space, 36. What's the probability of rolling 2 1s? 1 and a 1. Well, there's only one possibility there, right? That would be 1 out of 36, wouldn't it? Okay. How about the probability of boxcars, 2 6s? That again would be 1 out of 36. So rolling a 7 is more probable than rolling those other 2 numbers. In fact, 7 is the number that is most probable when you're rolling 2 dice. 6 and 8 are not quite as probable. All right, let's move on to our favorite topic, lotteries. Have you played the lottery? I never have, actually. But being a state employee and Florida has a state lottery, in a sense, I'm supported by the lottery, so I think they're quite important. And there's a lottery out there, Delaware's lottery, in fact, called the Multi-Win Lotto game. It works like this. If you want to participate in that lottery, you pick 6 numbers out of 35. So you have the numbers from 1 to 35, and you're supposed to select 6 of those numbers. You select 6 out of the 35. And order's not important here. You don't have to order those numbers. And if your 6 numbers match the winning numbers, you win the top prize, okay? Or you share it if somebody else also picked the same 6 numbers. So here's my question for you. What's the probability of winning the top prize if you buy 1 ticket? So you buy 1 ticket in the Delaware Multi-Win Lotto game. What's the odds of winning? What's the probability of winning? Let's figure it out. All right. So again, this is a combination problem because order's not important. And we're dealing with 35 numbers. So in a sense, we're dealing with 35 elements, and we pick 6 of them. So we're dealing with a combination of 35 elements taken 6 at a time. That's the sample space. All possible lotto tickets, which is 35 elements taken 6 at a time. Let's figure that out. So that's the size of the sample space. That would be n of s in our notation. And it's 35C6. Remember that notation for combinations? It's a capital C and there's a 35 on one side and a 6 on the other. It's a number, it's a calculation that's actually built into calculators, but we can at least show the numbers here right now. The numerator would be n factorial, that's 35 factorial, and the denominator is n minus r factorial, or 35 minus 6 factorial, times r factorial, which is 6 factorial. So it's 35 factorial divided by 29 factorial times 6 factorial. Okay, we know how to figure these out, don't we? We could do that trick of 35 factorial equals 35 times 34 times 33 down to 29 factorial and cancel. Let's not go through that again. I think we're experts on that topic. Here's the final answer you get. You get 1,623,160 possible lottery tickets. That's how big the sample space is. Pretty big number. Over 1.5 million different lottery tickets. So what's the probability of winning? Well, you select one ticket. You form one lotto ticket. It's 1 over that giant number. Not very good odds, are they? It would take a lot of tickets to get better odds. And again, I'm not sure how much these lotteries pay if you win. I know in the Florida lottery, there are some weeks where nobody wins, and then the prize is lumped in for the next week's lottery. And after a while, the prize can get pretty big, and then a lot more people start betting. Okay, let me pause here for a confusing question. This is something that's bothered me since I was a child. And maybe it's bothered you. You might think about this on your own. The weather forecast, how does that work? Not how do they predict it, not that's the weather maps and all that, but when they say something like the probability of rain is 40%, that's a statement I hear all the time. The probability of rain is 80% or 70%. What does that mean? Well, this is not a mathematics question as much as a philosophical question, but it's something that's always bothered me. Personal anxiety. To me, it's not clear. Do they mean that 40% of the time during that day it's going to rain? Or do they mean that 40% of the days, just like today, will have rain? In other words, and how much rain are they talking about? Does one drop count as rain? Does it mean that, well, I'm not sure what it means. And it's always been confusing to me. I do know the following. If they say the chance of rain is 10%, I'm not going to bring my umbrella. And if they say 90%, I will. But I'm still not clear what 90% means. Okay, personal problem, don't worry about it. On to some mathematics. Probability, where did it all come from? What motivated people to study probability? What's the history of this fascinating field? Well, I think you probably can guess. It came around from gambling. Probability arose because people were gambling, and they wanted to know the odds of winning. They wanted to figure out how to win in a game of poker or in a gambling event. And it turns out the gambler Chevalier de Muret, he posed some gambling questions way back in the 1600s. And two very famous mathematicians, Blaise Pascal and Pierre de Fermat, living in the 1600s, began to correspond and develop the ideas of elementary probability that we use even today. These two mathematicians made great contributions to the theory of probability. In 1657, the first book came out on probability, written by Christian Huygens, and he was a Dutch mathematician, lived also in the 1600s. And as I said before, this has grown not just from gambling, but it's now a field that permeates lots and lots of science and engineering. When you talk about, say, doing testing of new drugs on the market, there's a lot of probability and statistics built in there. What are the odds of this drug having side effects and things like this? You'll have a sample space of so many patients taking a drug. It's a big field. I highly recommend if you have a chance to study mathematics that you also consider studying probability. It's really fun stuff. Okay. Why don't you be the teacher for a moment? We've done a lot of these. These are kind of fun. And here's the question. Student comes running up to you, and you're talking about couples having children. And here's the question that you've posed to this student who is running up to you with an answer. So this couple intends to have 2 children. Okay, they want to have 2 babies. What's the probability they'll have 1 boy and 1 girl? And let's assume these are equally likely outcomes. So you want to have this couple wants to have 1 boy and 1 girl. What's the probability that that'll actually happen? Well, here's what the student comes up and tells you. The student claims that the probability is 1/3. And here's how the student argues. He says, well, the possible outcomes for these 2 children are both are boys, boy, boy, girl, girl, or mixed boy, girl. And there's only 1 boy-girl combination in there, so it's 1 out of 3. Sample space has 3 things in it. One of them is the boy-girl combination, so it's 1 out of 3. How do you answer that, student? What do you say? Is that student right? Is that the right answer? What do you think? Well, I claim that's not quite the correct sample space. Here's why. These children, you can sort of think that there's a first child and a second child. And the first child could be a boy and the second could be a boy. Or the first could be a girl and the second could be a girl. Or the first could be a boy and the second a girl, or vice versa. The first could be a girl and the second could be a boy. So I claim the sample space actually has 4 events in it, 4 elements in it. Boy, boy, girl, girl, boy, girl, and girl, boy. Those are different. Boy, girl is different from girl, boy. Okay, so now what's the probability of getting a boy and a girl? Well, it's 1/2 because boy, girl, and girl, boy are both successful here. Okay, so it's kind of a tricky little problem, I thought. All right, let's move on to a slightly more complicated situation with probability. We're going to talk about first mutually exclusive events and then complicate things a little bit. And I'll pose it as an example again. Suppose you have a standard deck of 52 cards. And if you remember, it has 4 suits, hearts, spades, diamonds, and clubs. And then you have the face cards, king, queen, jack, and then 10 down to ace. Okay. You select 1 card out of your deck of 52. What's the probability that that card is either a king or a queen? It's either a king or a queen. What's the probability of that? Well, the probability of being a king is 4 out of 52. There are 4 kings in a deck. And the probability of a queen is also 4 out of 52. And these are called mutually exclusive events. Kings are not queens and queens are not kings. There are no outcomes in common. So all you would do is add up 4 over 52. That's the probability of getting a king, plus the probability of getting a queen, and that's 8 out of 52. So that's the probability of getting a king or a queen. But suppose you have events that have an overlap. Here's an example of that we'll come back to in a moment. Suppose again you select a card out of your deck of cards. You select one. What's the probability that either it's a heart or a face card? Now you see why this is more complicated. The probability as a heart is 1 out of 4 because there are 13 hearts out of the 52. But some of those hearts are actually also face cards, aren't they? There's some overlap in these two. The jack, the queen, and the king of hearts are in a sense both face cards and hearts. So how do we handle this situation? If the events were mutually exclusive, like they were with that first example dealing with kings and queens, the probability of a king or a queen, the probability of the union of those 2 events, is nothing more than the sum of the individual probabilities, probability of A plus probability of B. But if there's that overlap, then the formula is slightly more complicated. The probability of the union of the 2 events is the sum of the probabilities, probability of A plus probability of B, minus the probability of their overlap, of their intersection. In a minute, I'll try to explain that in street language, why you should believe it. But let's do that example now. We go to our deck of cards, pick out a card. What's the probability it's a heart or a face card? Okay, so let's pin down the notation. Let's let event A being that the card is a heart. And that probability is 13 out of 52. There are 13 hearts in our deck. Let's call event B that the card is a face card. Now, how many face cards are there? There are 4 jacks, 4 queens, 4 kings. There are 12 face cards. So that's 12 out of 52. But some of those face cards are hearts. In fact, 3 of them are, right? The jack, the queen, and the king of hearts. So that overlap, that intersection is 3. And so the probability of those is 3 out of 52. And we have to take that off. In a sense, you're counting things twice. If you count it as a heart and a face card, you've counted it twice. That's why you subtract off the 3 out of 52. Here's a picture of the situation. We have sort of 2 sets here. One set is the set of hearts, and one set is the face cards. But these sets intersect each other. They have some common elements, the jack, the queen, and the king of hearts. And so there's an overlap here. That wasn't true when we were dealing with the king and the queen problem. They didn't intersect. Those 2 sets were, as we say in math, disjoint. All right, so let's answer the question. The probability of getting a heart, we discovered, was 13 over 52. The probability of a face card was 12 over 52. And the probability that it's both a heart and a face card, the overlap, is 3 out of 52. There are 3 cards that have both properties. So the probability of being a heart or a face card equals the probability of the first event plus the probability of the second event minus that overlap. So it's 13 over 52 plus 12 over 52 minus 3 over 52. That equals 22 over 52, which is about 0.42. That's your probability of getting a heart or a face card. Kind of nice, isn't it? Kind of interesting how that overlap comes into play. And I hope you see the reason for it is you've counted those 3 cards in a sense twice, and so you have to subtract them off. Okay, let's talk about the birthday problem. This is a great problem, and in order to get a handle on it, we have to first talk about one more probability idea. It's called the complement of an event. And it's very simple, so don't worry too much. The collection of all outcomes that are not in an event, not in the set A, is called the complement of A. And it's usually denoted A prime. And the probability of A prime is 1 minus the probability of A. So a complement is everything else. Let me show you a quick example. What's the probability of not rolling a 7 when I roll 2 dice? Not rolling a 7. Well, we don't have to add up all the possibilities. We calculated previously the probability of rolling a 7. It was 1 out of 6. So the probability of not rolling a 7 would be 1 minus 1 over 6 or 5/6. Wow, pretty simple, isn't it? It's everything else. 1 minus 1 over 6. All right. Let's do the birthday problem. And to set it up, let's talk about birthdays. So here's Fred. And the probability that his birthday is today is 1 out of 365. I'm assuming that the year is 365 days. So the probability that Fred's birthday is today is 1 out of 365. And the probability that it's not his birthday today is the complement. That would be 1 minus 1 over 365, or 364 over 365. A pretty high probability that it's not his birthday. So here's the setup that I've done this in class many times. You have a classroom, say, of 36 students. Okay, so they're out there, these 36 students. What's the probability that at least 2 of them have the same birthday? And again, we'll assume the year has 365 days. And you can do this with a class of students. It's kind of a neat experiment to do. They all tell you what their birthday is, and you find out whether or not 2 of them have the same birthday. Well, let's calculate the probability of that happening, that 2 students out of these 36 students have the same birthday. And to do it, we'll calculate the probability of the complement, that no 2 students have the same birthday. Here we go. You have this first student here, and then you look at the second student, and the probability that that second student has a birthday different from the first one is 1 out of 364 over 365. In other words, let me say it better. The probability that the second student has a birthday different from the first one is 364 over 365. In other words, one birthday is already taken. That's the birthday of the first student. So the second student has 364 other days that could be his or her birthday. How about the third student? The third student has a birthday different from the birthday of 1 and 2 with a probability of 363 divided by 365 because 2 of the days are taken, so there's 363 left over that could be different. The fourth student, I think you get the picture, now it's 362 over 365, and you keep going down to that 36th student, and 35 have already been taken. That leaves 330 over 365 that the student number 36 has a birthday different than the other 35. So, you have this giant string. The probability of the complement is nothing more than the product of all these probabilities we just calculated. 364 over 365 times 363 over 365, all the way down to 330 over 365. That's the probability of the complement, that no two students have the same birthday. And that turns out to be, on a calculator, about 0.168. So the probability of the event that two do have the same birthday, the complement of, we calculated the complement that nobody had the same birthday. So the probability that two of them actually do have the same birthday is 1 minus this number, and that turns out to be about 0.832. Whew. In other words, the probability is about 0.8, or 83% is your odds here. 83% of the time, two students will have the same birthday in this class of 36 students. Pretty high probability, even though there were so few students. In fact, if you do this analysis in a group of 23 students only, if you have 23 students out there, 23 people, the probability that two of them have the same birthday is slightly over 50%. And if you have, say, 57, a pretty big classroom, the probability is over 99%. So that's a great bet to make. You walk into the classroom and you say, you see 60 students out there, and you go, I'll bet you $1,000 against $1 of your money that two of you have the same birthday. And you've got pretty good odds you'll win. Okay, let's finish off with some practical questions, fairly simple with counting principles. You walk up to the ATM machine and you've forgotten your ATM number. What's the probability that you can guess it? That you'd punch in 4 numbers, it's a 4-number ATM number. What's the probability that you'll guess it right? Well, yeah, there are 10 to the 4th possible numbers, and your odds of guessing it are 1 out of 10 to the 4th. And if you happen to know the first 2 digits, then of course it'd be 1 out of 100, 1 out of 10 squared, or 0.01. Good, okay. Kind of a fun class, I think. I really enjoy probability. I think it's got great problems. It's got some subtleties, but it's a lot of fun, and I hope you'll find the chance to study some more probability if you have some free time. It's, again, a vast area of mathematics. So what are we going to do in our final lecture 36? I'd like to do 2 things in that lecture. One is look at a really neat device, the magic device, I think, the Global Positioning System device, a GPS device. I've got one in my car. How does it work? Well, I'll try to explain that next lecture. And then I'll also turn to a little bit of calculus. Remember, this course is called pre-calculus. So what's calculus about? Now, we've seen some calculus ideas already. I've tried to slip some in here and there. We've seen this idea of limits and stuff like that. Well, I'll show you another calculus idea next lecture to try to whet your appetite and to encourage you to go on and study calculus. So see you next time. Thanks.